It's an honor to be here and share some research findings in our group. And I'm Huiqi Deng, assistant professor at Xi'an Jiao Tong University. And my research focuses on explainable AI, which aims to enhance the interpretability and transparency of AI systems. If you are interested in explainable AI, please feel free to reach out to me. And first, we will begin by introducing some key challenges faced by explainable AI. The first is the reliability of explanations is questionable. First, the faithfulness of explanations is difficult to guarantee because we do not have the ground truth of explanations. We can see this picture. Many popular methods may produce exactly the same explanations for different classes, such as the cat and dog explanations. And the second is it's difficult for an explanation method to provide a complete picture of modern reasoning. We can see that current techniques can only identify which regions is important for classification, but they do not clarify which specific features within this region the model will rely on. And the second challenge is explanations often fails to guide the debugging optimization of DNNs, although a few studies try to bridge this gap, but their core hypotheses, such as smoother explanations, can improve model robustness, like both theoretical and empirical validation. So our group found that game-theoretical interactions can address the two challenges to some extent. So what are game-theoretical interactions in the context of deep learning? They actually represent the cooperation relationship between input variables encoded by DNNs. For example, in face recognition, we can see that the interaction means the cooperation between eyes, nose, and mouth features. And in NLP analysis, it's the cooperation between words like never, fails, and impress. And these interactions will make a numerical effects on the network outputs, which can be quantified by game-theoretical interaction metrics. And we found that these interactions can explain inference logic of DNNs more faithfully and comprehensively. First, unlike classical method, which can only quantify the contribution of each individual variables, it captures the complex interactions within DNNs. We can see that the output can be decomposed into the sum of interaction effects, and it captures the interactions between never and impress, and the double negation between the never, fails, and impress. Second, it naturally corresponds to the completely functional decompose of DNN. Third, we found that it reveals the common mechanism of popular attribution explanations. Moreover, due to the functional decomposition properly, we found that each interaction can serve as an elementary inference pattern of DNNs. That means the overall performance of a DNN can be decided by the combined effect of all interactions. And we found that the difficulty of learning different interactions increases exponentially with their complexity level. And the poor generalization of DNNs often relates to more interaction patterns, and adversarial attacks may disrupt these complex interactions. And finally, the takeaway messages is interactions can both provide a more faithful and comprehensive explanation, and can enable debugging and optimization of DNNs. Thank you.